a very good day. My name is Tirichoran, like you see, and my metric series MA19091. So now I would like to start the introduction for our boundary layer experiment. So boundary layer is a thin layer of fluid that forms immediately around a bounded surface as a result of fluid flowing over the surface. As you can see the beside picture, there is a wing which is subjected to boundary layer due to fluid flow. So this is an example of real life where the boundary layer is formed on an object which is subjected to fluid flow. So boundary layer is formed when the fluid is said to be viscous. In terms of fluid dynamics, the boundary layer is defined as the area where the flow changes from zero velocity to maximum velocity in the flow stream. So the concept of boundary layer was brought in by Ludwig Prandtl. Ludwig Prandtl was the first individual to propose the theory that explains the boundary layer's effects. So although the general equation before these had been known, their solutions did not apprehend observable flow phenomenon. So Ludwig Prandtl was the first one to notice this, and it rendered the idea where the relative strength of the inertial and viscous altered from a layer very close to the surface to a region far from it. So via this concept, he proposed the boundary layer concept, and he rendered this idea to this world. So boundary layer formation in real life. So there are many boundary layer formations and many types of boundary layer formations in real life. So now the first one is when an aircraft wing is subjected to fluid flow, the area of the flow near the plane wings where viscous force causes the surrounding non-viscous flow to deviate is known as the velocity boundary layer. So this is an example of boundary layer. Second, the formation of atmospheric boundary layer occurs close to the ground or 100 meters away from the Earth's atmosphere. So the third type of boundary layer is the thermal boundary layer. Thermal and velocity boundary layers are formed when the heated air near to a person causes gravity-induced convective airflow. So another type of boundary layer flow or the boundary layer formation is through aerodynamic drag. So these are the real-life examples of boundary layer formation. So let us come back to our experiment. There are several objectives that we like to achieve in this experiment. So the objectives are to investigate the behavior of the boundary layer over the flat plate, to understand the relationship between shear stress distribution and the velocity gradient of the boundary layer. Finally, is to determine the velocity distribution for smooth surface plate and rough surface flat plate. So our idea is basically revolving the roughness of flat plates. So the scope of our experiment. So the typical type of flow that may be observed in many engineering processes is the movement of boundary layer. Hence, through this study, it is essential to determine the speed distribution of flat plates according to their roughness. So in this experiment, we are basically determining the speed distribution according to the surface roughness of the flat plate. So we used a HM225.02 boundary layer apparatus in the combination of HM225 air flow bench, and the methodology and procedure will be explained by my other group mates. So the data obtained is then collected and analyzed for enhancing the study of the boundary layer conditions over a flat plate. So that's all for now. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arif. My number ID is MA19050. Today I'm gonna present to you about the experiment E21. Okay, first we go to the literature review of chapter 2. There is fluid flow. There is branded boundary layer. Next, we go to the first point. There is fluid flow of a solid body, and the velocity of the boundary stays zero only if the boundary is stationary. Okay, number 2, the boundary layer developed in 3 stages: laminar, turbulent, and transition. Number 3, boundary layer theory determine aerodynamic drag Fd and aerodynamic lift AR. After the boundary, there is no velocity gradient du over dy, since the outside boundary layer velocity is equal and constant to the free stream velocity. Okay, this is the example figure for the boundary layer. And next, we go to the law of the conservation. There is begun with 2 fundamental physics principles. There is mass conservation and the momentum conservation. Okay, this is the boundary layer over the flat plate. this is example of the feature. Okay, that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I am A1919 Muhammad Iqbal Haikal bin Ibrahim. So today I want to present about my part. So in the experiment we have the methodology. So I want to present about this. First is apparatus. So as you can see, this is a boundary layer apparatus HM225A flow bench. So I want to tell you about every single part of this. First, laboratory trolley. Number 2 is switchboard, bench top, manometer panel, and number 5 floor straightener. Seat is the nozzle. 7 receptacle for the accessory module with measuring gland. Number 8 is thermometer. Number 9 is regulator flap. Number 10 is feed pipe. And number 11 is outlet pipe with hood. And lastly is number 12 is radial fan. So next, this is a flow over flare plate. So in this experiment, we use the groove plate and smooth plate for the material. So as you can see in the picture, this is a different plate. Next is experiment setup. So as you can see, this picture is a boundary layer experiment setup. So the last part is the experiment procedure. For experiment procedure, when we run the experiment, we have our procedure to make sure the experiment will be run with complete and successful. So the firstly is the current air density was determined by measuring the ambient temperature and air pressure with a thermometer and a manometer. Second, the smooth surface flat plate was pushed to the position S equal to 10 mm and secure it with the Nelly screw. Third, the reference level for ambient pressure was read by using the manometer. And the fourth, the one channel read up to the desired speed. For this part, we set it on the precision regulator at 7 to 8. Number 5 is pitot tube was moved close to the plate and the first measure value for dynamic pressure was read off. Next, the procedure was repeated by using the other position is S equal to 20 mm to 80 mm, as you can see at this procedure. And lastly, the step 2 seats will be repeated using a rough surface plate. So this is a procedure, experiment procedure for our experiment. So that's all from me. Thank you.
Hello everyone, my name is Madhavan son of Sivaraman at TKD MA18090. Today I would like to talk about the results part of our experiment 2, part 1, which is boundary layer. Now let us look on the data for smooth surface. So first of all, we need to plot data for plate distance, boundary layer thickness and height. All these values are in mm, and then we will find the average height, which is from this value 249 we added till 213, which is we having 8 values, and then we find average by divided by 8. So for the velocity, we will find by following this formula, which is 2 gravity times with delta h, difference in height. So for the difference of the height, we will calculate by minus initial height with height that we find here, and so we will get the value of 52 mm here. Then we will substitute this value in meter to get the velocity respectively. Now let us look on the rough surface. Same procedure as we done for the smooth surface, but we will do for the rough surface. For this value, we get a value which is a bit higher, that is 55 mm, and then as usual we will substitute this 55 mm into the velocity formula to get a new velocity. So these are again we plot the data for the plate distance, height and also the boundary layer. We also find the average height and also the velocity. So now let us look on the velocity distribution of smooth surface. So this graph represents the trend of this velocity movement along this boundary layer. So let us look on this trend. As we can see, from the plate distance which is 10 till 50, we can see a rise, and also from 50 to 60 plate of distance we can see a constant value which is the constant velocity of distribution, and also a increase, and after that a decrease when reaching the plate distance which is 80. For the rough surface, there is an increment at first from 10 plate distance, and then there is also a decrement at the 40. Then we can see a maximum rise up till plate distance 80 mm. So this is basically for the rough surface velocity distribution. So that's all from me. Thank you.
My name is Muhammad Daniel Muskifli. I will be presenting for the discussion for this experiment by answering the questions from the lab sheet. The first question is, explain the boundary layer thickness in the boundary layer of both surface. So, the boundary layer thickness for rough surface should be thicker than the smooth surface. This is because surface roughness is directly proportional to the boundary layer thickness. So, as the roughness of the surface increases, the thickness for the boundary layer is also increases. The theory behind this is that increasing the surface roughness will increase the friction resistance coefficient, which prevent the fluid to flow in its direction, which will cause the boundary layer thickness to be thicker. Okay, next question is, what is the distance in the plate before the flow becomes turbulent, and what phenomena could be the reason of these changes? Okay. For a flow to become turbulent, it depends on the Reynolds number. This is due to the fact that Reynolds number is used as an indicator whether the flow is in laminar or turbulent or transitional. The Reynolds number for laminar is lower than 2300, and for turbulent is 4000 and above. So to find the distance where the plate before it becomes turbulent, we need to find the distance where Reynolds number is below 4000. So to calculate Reynolds number, we will use this equation. Reynolds number equal to density times velocity times length divided by the dynamic viscosity of the fluid. So the phenomenon that causes this is due to the increases in thickness in the boundary layer. In the turbulent flow, swirls are formed and the motion of fluid is disturbed, which creates the turbulent flow in the boundary layer. The last question is, what are the differences in terms of result for smooth and rough surface? From the result, for the smooth plate, the velocity increases from 0.0118 millisecond to 0.0129 millisecond when the plate is increased from 10 to 80 mm. As for the rough surface, the velocity increased from 0.0109 to 0.0123. So we can say that the rough surface slows down the flow velocity compared to the smooth surface. So this is because the velocity in smooth surface is higher than the surface roughness. The Reynolds number for smooth surface will also be higher than the rough surface.
So now I would like to continue the conclusion of our experiment. So as the experiment was conducted, we learned and studied the methods via the collected data to determine the speed distribution for flat plates and the boundary layer thickness. So based on the experiment results, a smooth surface flat plate rendered a higher flow of flowing fluid than a rough surface flat plate. So this is one of our conclusion. And in terms of boundary layer, based on the experiment results, a smooth surface plate rendered a higher flow of flowing fluid. So hence, from this experiment, we can conclude that the surface roughness will influence the boundary layer conditions, as the boundary layer conditions will, be influenced by Reynolds number. So why is it influenced by Reynolds number is due to the significant viscosity effect and higher shear stress on the rough surface. So according to the discussion, the speed distribution between the smooth surface plate and the rough surface plate has been compared along the different thickness, and the objective is said to be obtained. Thank you.